Welcome to Data Science with EJD. In this video, we take the first algorithm as far as unsupervised learning is concerned, and that is K-means clustering. Just like we know already, one of the key algorithms under unsupervised learning is clustering, and then of course later on. So I'm going to take series of algorithms under clustering, and then from there we move on to dimensionality reduction and other things that we may have to consider under unsupervised learning. So introduction to clustering is the first thing we have to look at here. Um, Clustering is an unsupervised learning technique used to group data points into clusters based on similarity or distance. Unlike supervised learning, clustering does not use labeled data. So K-means is one of the most popular and efficient clustering algorithms, particularly suited for numeric and continuous data, right? So that's our introduction to clustering right there. So K-means clustering, an overview of that. So the objective of K-means clustering is to partition n observations. Say we have 1,000 data sets, or data points, so to speak, and want to partition that into K clusters. You can choose K to be 5 clusters or 2 clusters or 3 or whatever you choose, in which each observation belongs to the cluster with the nearest mean or centroid, right? Minimizing the intra-cluster variance or inertia. So each observation belongs to the cluster with the nearest mean or centroid, right? The key assumptions here are the following. Clusters are spherical and equally sized. Then data is numeric and continuous. Then the number of clusters K is known a priori. Like you get to decide the number of clusters ahead of time. I believe that's what that means. Then core conceptions and intuition. First of all, we talk about the idea of centroids. Since you're clustering, so it's more like you're grouping things in their in particular wherever they are, you're grouping them together based on certain behavior. So each cluster is defined by a centroid. That is the arithmetic mean of all the data points in the cluster. Centroids are recalculated at each iteration. Then you have what you call inertia, which is uh, uh, you can use within cluster sum of squares for that. WCSS measures, so the within cluster sum of squares measures compactness of clusters, right? That's it for inertia, right? So inertia is summation from I equals 1 to K and summation for S belonging to Ci of the difference between X and mu I all squared. So lower inertia means more compact clusters, but lower inertia with higher K is not always better due to overfitting. Then apart from centroids inertia, we can also talk about convergence. All right. K means converges when either the cluster assignments no longer change. So if you keep iterating and the cluster assignments no longer change, then you have reached a point where the clusters do not change. So the centroids also stabilize. So the change is below a tolerance threshold, and then you have a maximum number of iterations is reached. So that's when there's a convergence. So K-means is guaranteed to converge, but only to a local optimum. So you always expect convergence for K-means. Now, the K-means algorithm, step by step, what do you do with the K-means algorithm? So the first thing is you initialization. So you choose K initial centroids randomly or using K-means plus plus. So so you choose your number of clusters. That's all that is talking about. Then you have the assignment. So you assign each point to the nearest centroid, like an Euclidean distance. All right, so you may do that distance between 2 points. Then update, you recalculate centroids as the mean of the assigned points. Then you can repeat steps 2 to 3 until convergence is reached. So it's an iterative process for sure. You do that using the Lloyd's algorithm. Okay. Then number 5, how to choose K. How do you decide the number of clusters you choose for a particular data set? So since K is a hyperparameter, a hyperparameter is something you can tune to get the best result from your data set. So since K is a hyperparameter, it must be selected using evaluation metrics. So, and to do that, you can use the elbow method or the silhouette score. So for the elbow method, so here you can plot K versus the inertia. Then from there, you now find the elbow point where inertial reduction slows. The elbow suggests the optimal trade-off between compactness and simplicity. All right. And then you have the silhouette score, which measures how similar a data point is to its own cluster versus other clusters. And that is the silhouette score is calculated by B minus A all over the maximum between A and B, where A is the mean intra-cluster distance and B is the mean nearest cluster distance. And the range is usually -1 to 1. So your silhouette score is bound to be somewhere from -1 to 1. So if it is one, it is well clustered. If it is zero, it is on the boundary. If it is less than zero, it is misclassified, right? So that is silhouette score. So we're always expecting a silhouette score as close to +1 as possible, right? We don't want negative values of silhouette score because that would mean we have a misclassification. All right. Other methods exist like gap statistic, which compares clustering performance with random reference data. You also have the Davis-Bouldin index and the Kalinski-Harabas score. Yeah. Having said all that, can we look at a Python implementation using scikit-learn? So you see, scikit-learn is so robust. It has helped us with supervised learning, dealing with so where we've had classifiers and regressors. Now we're coming to talk about cluster. We're talking about things that help us with clustering, algorithms for clustering, models for clustering. So step-by-step example now. So of course you want to import the necessary libraries like NumPy, Matplotlib, and then some special things from scikit-learn, like data sets you make blobs. I mean, this big blob, I think it helps us to generate synthetic data. Then you can have sklearn cluster. From there, you bring KMeans, which is the model we are using here. Then the metrics here, you can use silhouette score as a metric or elbow method. So we're using silhouette score here. So you can generate synthetic data from this make blobs now. So you have X, Y true, make blobs, n samples, you want 300. So you can change this as you want. Then the centers will be 4. Then the cluster standard deviation, I believe, is 0.6. And the random state is 42, right? So centers so it means you're going to have like 4 clusters. That's basically what this is talking about. So to visualize the data, you can do this. So you can plot the scattered diagram for this and to show you the synthetic data you're working with. So I'm trying to run that, so it's taking a bit of time. Now it's here. So these are the this is the data you have now. It's synthetic by the way, so it's nothing. In the next video, I'll be dealing with something in particular, talking about customer segmentation. So this is the data we've got. Then the next thing is how do you choose the number of the value of k, I think. So of course I did the first 5 lines is just there to there's the one I was getting when I ran it, so I have to put this in place to avoid that warning. So but beyond that, we need matplotlib to visualize, and we need k-means to do this. So inertias, you initialize it for inertias. The k range is from 1 to 10. That's what you have chosen. You can change it if you like. So you now say for k in k range, km is now k-means number of clusters is equal to k. Our job here is to know the number of k's that really make sense. Then the initialization is about k means plus plus, and the random state, of course, this guarantees reproducibility, and then you can now fit the model, for that x that we have done up here, and then you can plot that. Talking about the elbow method now. So you run this. So what this is telling us is that this is coming down. So around here now you have the idea of the elbow, like we saw before, is where the thing begins to slow down. For me, if you are going to pick number of clusters, it should be either 3 or 4. Most likely 3, because from 3 things begins to slow down and then everything is just flattens out like that. So most likely, if you're going to pick number of clusters for this, should be 3 or even 4, where the thing settles down. Okay, then we have silhouette analysis. We can use silhouette analysis also to determine the value of k that we need. So silhouette scores initialize that. So for k in range 2 to 10, km is k means, so we are declaring the model we want to use. Labels km fit, you are predicting with x, then the score, silhouette score x, and label silhouette scores dot append, because you have initialized it, so the scores will keep coming here. And then you can also plot, you can visualize that to see the number of clusters like that. Okay, so we see all of this. So you see again that the top value is also around 4 here. So that means the silhouette can be something like 4, uh, you know, so the K can be around 4 because it's like the peak value around here. So with all of that done, then we have seen that the optimal K is 4, using both elbow method and silhouette score. So we can now go for the final cluster where we now say, okay, optimal value of K is 4. So K means n clusters is equal to optimal K, which is 4 actually. Then you have all of these things. Then you can now predict. So the labels you now predict with K means, and then you plot this to see the clusters. So if I run this now, of course, here, we have the centroids, which talks about the center of the cluster. So with this now, we have those 4 clusters here. This is a made-up data. It's synthetic in nature, but that's how it goes. In the next video, I'll be doing something. I'll be using some real life data. So what are the strengths and limitations of this? First of all, the strength. It is simple and fast because it scales well to large data sets, and it works well when clusters are compact and spherical. Like what we had up there, the clusters are very compact, they're very close by. Then it's easy to implement and interpret. The limitations, it requires predefined K. So, you have to decide the kind of K you want by either using the elbow method or the silhouette score to know the optimal value of K for each type of data set. Then it is sensitive to initialization, solved partly by K-means plus plus. And it is also sensitive to outliers and noise. It is sensitive to non-spherical cluster shapes. Only supports Euclidean space, not great for categorical data. So if you're working with categorical data, K-means may not give some reliable results. And that's why we have other algorithms that we're going to be considering later. So talking about best practices and tips, you have to standardize features before clustering, especially with different scales. Then you use multiple random initializations to avoid poor local minima. Always validate cluster quality using internal evaluation metrics. Then compare with other clustering algorithms like DBScan, agglomerative clustering, etc. We're going to consider this one after the other in the subsequent videos. All right. So talking about the conclusion now, um, K-means is a foundational clustering algorithm in machine learning. Its simplicity, okay, I guess I want to also break this up so that we can, easily see it in one blow. Okay. Yeah, I think this works. All right. K-means is a foundational clustering algorithm in machine learning. Its simplicity, scalability, and efficiency make it a strong choice for many tasks, especially as a baseline. However, careful selection of K, consideration of data structure, and evaluation with proper metrics are critical for meaningful results. So with this, we come to the end of this video on K-means. In the next video, I'll still be talking about K-means clustering, but it's, for customer segmentation. So we want to group our customers to see, we want to cluster our customers basically. All right, let me know how helpful this video is for you. If you have subscribed to the channel, thank you. If you have not, please go ahead and subscribe and be sure to hit the notification bell so you can always get alerted each time a new video is released. All right. If you, I mean, I also have membership on my group, my channel, YouTube channel. You want to become a member to see, to get some special benefits. You can explore the perks. Then, of course, all my code sheets and maybe slide presentations and data sets, they're all available. Just follow the description box in YouTube or even on Facebook. Click the link. It will take you to a Google Drive where you can actually download all data sets and code sheets. In fact, I always advise you do that first and follow step by step. So as I work, you follow me, you follow along. If you see a number somewhere, try to change those figures and see what the impact is in a particular code you're running. So that's how to run, because I believe the best way to code is the best way to learn coding is to code, basically. All right. So let me feel free to like and share the video also so that more people can have access to this great channel. Till I come your way again, keep doing data right. Bye.